Hey guys, my name is Pedram and I'm a professional practice assistant professor in finance. I'm also a CFA charter holder. This is another episode of my crash course in machine learning concepts, simply explained. Alright, part 35. In this episode, we're going to talk about boosting algorithms, namely AdaBoost, gradient boosting machines or GBM, and then finally XGBoost. Okay, this is going to be our last episode of going over supervised machine learning algorithm. In the past few episodes, we've been talking about tree-based regression and classification models. We started with decision trees and we talked about how powerful they are in terms of interpretability and how simple they are when it comes to visualizing things, right? However, we said that these decision trees alone are not the best performers out there when it comes to comparing machine learning models. So we talked about the advantages and disadvantages, and we emphasized that there are lots of advantages about decision trees that we love these models. However, we want to fix the caveat of the low performance of these models. So for that reason, we extended the idea of single decision tree to joining them together and make it ensemble method, right? So we talked about bagging and random forest, which is the ensemble method of the decision trees. Basically, this means that we are combining lots of decision trees as weak learners to come up with a strong learner, right? So the idea is that why not take advantage of the wisdom of the crowd? So with that, with bagging and random forest, we were able to reduce the model variance, and then basically it means that we were able to get a more accurate model. Today, we're going to talk about boosting. So the goal in boosting is pretty much the same as random forest. The idea is that how can we reduce the model variance and take advantage of that power of the decision trees model. So the boosting is going to do the same job. It's going to reduce the model variance, but in a different way. So let's talk about what's the difference between bagging and boosting in this episode. Okay, so let's talk about bagging versus boosting. Uh, as a reminder, what is bagging? Bagging consists of creating many copies of the same training data. So this is your training data, and we're going to make multiple copies. So this is copy number 1, number 2, number 3, and we can have capital letter B of these copies. So this is the number of bootstrap, right? Number of trees that you can make. And each copy is slightly different from another, right? And then we're going to apply the weak learner algorithm to each copy. So our weak learner here is going to be decision tree. So here I have decision tree number 1, decision tree number 2, and etc. Right? So these are going to be our weak learners. And we do that, we combine them to come up with an ensemble method. And that ensemble method is obtain multiple weak models. And hopefully we're going to get one stronger model out of that, right? So the idea is that this weak learner number 1 is going to give us one prediction. Let's call it f hat 1, number 2, f hat 2, and etc. We are going to have f hat b. This is the number of bootstrap that we have, right? Of these outputs. And now, depending on if you're dealing with a regression model, we can take the average and aggregate. If you're doing classification model, we can look at the majority vote and again aggregate. The idea is that in bagging, the bootstrapped trees are independent from each other. So this is important. So this means that this tree number 1, when we have that, we are done with this tree, right? We make predictions and we're done with that. Then we have another tree that's coming off of the original train data set. So we have tree number 1, we make predictions, done with that. Tree number 2, we make predictions, done with that, and etc. All these capital letter B trees are independent from each other. So this is very important. And when I say the trees are independent from each other, don't get me wrong, I don't mean that they're not correlated. Remember, in random forest, we said that the trees are correlated with each other, and the random forest was trying to decorrelate them, right? So they're going to share lots of observations, share lots of features, but the idea is that when you're constructing tree number 2, it has nothing to do with tree number 1. So that's what I mean by independent. So this is bagging. Now, what do we mean by boosting? So boosting consists of using the original training data. So this is the same training data that you're dealing with, and now iteratively creating multiple models by using a weak learner. So let's say we start from here, right? So we're going to say, okay, this is a slight variation of the data, and then we're going to make our model, let's call it decision tree number 1. This is our weak learner, right? And that model is going to make some predictions, right? Let's call it f hat 1. And whatever is explained, it's going to be passed toward the final output, and whatever is not explained is going to be passed as a new data set, right? So this is your, let's call it residual. So the residual is going to be passed to the second data set, right? So the idea is that each new model will be different from the previous one in the sense that the weak learner, here the decision tree, by adding each new model tries to fix the errors from the previous model, right? So whatever is explained goes to here, whatever is not explained goes to the new data frame. And guys, pay attention, this data frame is different from the original data frame. So it's not slightly different, actually it's really different, because your target variable here is going to be the residuals, right? Residuals from the decision tree number 1, from weak learner number 1. Okay. And then we're going to apply, this process is sequential. We're going to apply another decision tree, let's call it DT2. Whatever is explained is going to be passed to the output, let's call it f hat 2. Whatever is not explained, again, as a residual, goes to the third variation of the data, right? And this continues until, let's say, we repeat this process capital B letter of time. So this is not bootstrapped. This is just a number, right? So you can, for example, do it 100 times, 200 times. And then all these residuals are going to be added together. Okay. So in boosting, each tree is grown using information from the previous tree. So this is the main difference between bagging and boosting. Remember, in bagging, the trees, the process of building the trees were independent from each other. In boosting, actually, they depend on each other, right? When you want to make the second tree is going to be built on top of the residual of the first tree. So this is a first difference between bagging and boosting. Another difference happens in the aggregation. So in bagging, let me use red. So in bagging, this is how the aggregation happened, right? So we said if it is regression, we're going to take the average. If it is classification, we do the majority vote. In boosting, however, the aggregation process is different. It's not going to take the average or the majority vote. We are going to, the final prediction is going to be a combination of the previous runs, right? We're going to add them together. So for example, this is your f hat, let's call it boosting. This is the final prediction of the model, and it's going to be a function of f hat 1. So this is whatever we got from here, and then plus some coefficients of the following models, right? Let's call it lambda f hat 2, lambda f hat 3, and etc. Right? So these are some shrinkage parameters, and you're going to do this for let's say 100 times, 200 times. So as you can see, the aggregation happens as the summation. So we are not taking the average anymore. So these are the main differences between bagging and boosting. So to summarize, in terms of aggregation, they are different. And in bagging, we are doing bootstrapping on the same data set, make different copies that are slightly different from each other. In boosting, we are not doing bootstrapping, right? So maybe the names are a little misleading. So boosting, we are not bootstrapping. We are making trees in a sequential order. Each tree is built on top of the residual of the previous tree. So this is the main idea of bagging versus boosting. Okay, in the next few slides, I'll be talking about 3 different boosting models: AdaBoost, GBM, and XGBoost. So the goal is to familiarize you with the big picture of all these models and hopefully make you motivated to go ahead and read the mathematics behind them. But for now, let me actually show you how these models work, and then you will see how beautiful and how neatly they are designed. Okay. So let's start with AdaBoost first, or adaptive boosting. So this is a classification example, but the narration for regression is going to be pretty much the same. So AdaBoost is a boosting model, so it means that it's a forest of weak learners. So we're going to have a bunch of weak learners, right? And our weak learners, as always, in these boosting methods are going to be decision trees. And each decision tree is a tree with only one feature. So this is important. In AdaBoost, your weak learner has only one feature. So basically, it's this stump. It's not a tree, right? So let's look at that. Imagine this is our classification problem. We have 5 blues and 5 reds. This is a very simple example, right? And each tree that we're going to make in AdaBoost is going to depend on the errors from the previous tree, right? So in that sense, they are not being independent, right? So each tree depends on the error of the previous tree. So imagine this is our train set that we're going to start with. And then what are the steps? We start with our usual splitting criteria. If I give you this data set, right? If I give you this data set and then ask you, okay, what are the, with your weak learner algorithm, which is decision tree, what are your options? So remember, you have to start by answering those two important questions in regression, in decision trees, right? What feature to start with? Where to put the split? Imagine this is your feature number 1, this is your feature number 2, and what feature to start with where to put the split. And let's say you have two options, right? And you can go ahead and calculate the decision tree criteria for each of them. You can calculate the Gini, you can calculate the entropy, or whatever makes sense, right? So here for an exercise, let's go ahead and calculate the Gini index for each of these splits, right? So if you calculate the Gini for this split, you should get something around 0.375. And if you go ahead and calculate the Gini index for this split, you will get, let me write down the number, 0.416, right? So we know that the algorithm is going to pick the split, which is going to generate the smallest Gini, right? So the algorithm is going to pick this split. So we're going to start with this. I leave this one as an exercise. This is very easy. You know, mathematically calculating that, it's very easy. We have done this before for a more complicated numerical example. So if you're interested to see how it's done, watch the previous videos that I talked about how to calculate the Gini and entropy and classification error. So for the first tree, we're going to start with this split, right? So this is our split number 1. Okay. And then let's go to the second step. Second step, each tree, or in this case stump, gets different weights based on its prediction accuracy. So look at that. We have a tree, and then this tree is going to give us an f hat. Let's call it f hat 1 for tree number 1. And so this is classification problem. So we can report accuracy, precision, recall, and etc. So whatever that performance metric is, let's say work with accuracy. We're going to weight this model, this tree number 1, with that prediction accuracy. Let's call it weight 1. I'm going to use capital letter W, weight 1. Okay, so this is the first weighting that's going on in AdaBoost, right? So we're going to say, okay, tree number 1 has weight W1, and that W1 corresponds to the prediction accuracy for tree number 1. Okay. Then there's another weighting going on behind the scene. So that weighting is weighting of the observations themselves. So let me use black. So the weighting of observations. So each observation is going to get a weight inversely related to its prediction outcome. So look at this split. Anything to the left is called blue. So these are good observations. So the weight is going to be a smaller, right? Because they're not misclassified. Remember, the weights within each tree for each observation is going to be inversely related to predicted outcome. So these are correct classification. The weight is going to be small. On the right-hand side, everything is going to be classified as red. Again, these are going to be good classifications. So we're going to give them less weight, right? In the next tree, right? But look at these ones. So let me use red. These ones are misclassifications. These 3 blues are classified as red, and we know that it's wrong. So in the next tree, we're going to exaggerate these ones. We're going to give them more weights. Look at the, at least visually, look at the magnitude of the pluses, the blue pluses. They're larger compared to the rest of the observations, right? The rest of the observation, because in the previous slide, previous tree, they were classified correctly, we're going to give them less weight. And for the misclassified one, we are going to give them more weight. Why? Because remember, the whole idea of boosting, we want to fix the upcoming trees based on what was going wrong in the previous tree, right? So in tree number 1, this is what was going wrong, these 3 observations. So we're going to focus more attention on them. So that's why we're going to give them more weight. So visually, actually, it seems that we can make the pluses larger, but mathematically for computer, how do we do that? we're going to simply repeat these observations more in the new tree, right? So this is how we exaggerate these observations in the new tree. So in tree number 2, we're going to have more of these observations. Okay, so this is how we exaggerate them. Okay, so then we're going to construct the second tree. It's going to be in a stump. And then if you look at the second tree, this is going to be the best split, right? So for second tree, we have another f hat 2. And based on the prediction of the second tree, we're going to give it another weight. So this is weight number 2. And so just in parentheses, the process for regression is pretty much the same. So the idea is that whatever is not explained, the in the first model, we are going to give it more weight in the second tree, right? So let's say we calculate the errors, and we are going to give more weights to the observations with higher errors, right? So that's how it's done in regression. For classification, you see you're seeing how it's already done. Okay. Then we say, okay, now I want you to pay attention to this tree number 2. So in tree number 2, these are going to be correctly classified, and this is going to be correctly classified, and also these are going to be correctly classified. So what are the misclassifications in tree number 2 are going to be these 3 observations. So these 3 observations are going to be exaggerated in the next tree. Look at that. So they are exaggerated in the next tree. Exactly because we are trying to fix the errors from the previous model, right? So these are going to be exaggerated, and the rest of the model, the rest of the observations are going to get less weight. So based on that, we are going to come up with our third tree. Let's call it f hat 3. And then based on the prediction of this third model, we're going to give it some weight 3. And we're going to repeat this process many times, right? At the end of the day, we're going to aggregate. We're going to aggregate each, all the trees based on each weak learner's weight, right? So we have W1, in this simple example, W1, W2, W3. It's as if we are putting all these classifiers together. Okay, so this is how it's done. So the aggregation is basically the summation of the weights and over all the models. So that's the idea of AdaBoost, and I hope you get the big picture of how it's done both for classification and regression. So the idea is that to give more weight to whatever is not explained in the first tree. And there are 2 weightings going on. We are weighting the models themselves based on their performance, and we are weighting the observations as well based on how accurately they have been predicted or not, okay? Or what was the error rate, how far they were from the true observation, if it is classification, if they were misclassified. Okay, the next one is going to be GBM. So what is GBM, or gradient boosting machine? In gradient boostings, each weak learner, in this case decision tree, correct its predecessor's error. So that was the main goal in all boosting algorithm, right? We want to correct whatever is left unexplained. But there are a couple of differences between GBM and AdaBoost. So let's go over them. So for this one, I'm going to work on a regression example. This way you have seen both AdaBoost and GBM for classification and regression. The first difference is that unlike AdaBoost, the weights of the training instances, the observations, are not tweaked. We are not giving different weights to the observations themselves. Instead, each predictor is trained using the residual error from the previous tree as labels. So let me tell you what I mean by that. So imagine you start from this train set. We have X and Y. And this is very simple 2-dimension data, right? So there is one feature and one target variable. Then you're going to build your first decision tree, and you're going to make some predictions, and the predictions are going to be depending on the depth of the tree, are going to be some, actually this is going to be a step size function, right? So if you have something like this, if you have, let's say, maybe we get something like this for a tree. This is a regression model of a tree, right? And then we're going to come up with some predictions. So we have Y and Y hat. We're going to save the residual. So let's call it the residual from number 3, R1. So R1 is going to be equal to Y1 minus Y hat 1, right? And the main difference is here. So we're going to say that, okay, take this residual as the new target variable in the second tree. So in the second tree, we are going to work with the same feature, but the target variable is different. Target variable now is going to be residual, whatever is unexplained. Then we make another decision tree based on that. We make some other predictions. So we have R minus R hats, right? This is just like Y minus Y hat, but because we're regressing it on residual, so let's call it R1 minus R1 hat. So this is residual number 2. Again, some part of it is going to be not explained. Whatever is not explained is going to be passed to the third weak learner. So third weak learner works with the residual from model number 2 or weak learner number 2 and the same feature. And this process is going to repeat, let's say, n times. So we have n trees, and lastly, this is a residual from the nth model. Right? So this is the first difference between AdaBoost and GBM. So in AdaBoost, we saw that each observation is going to be weighted differently. It's going to be weighted inversely related to the predicted outcomes. But in GBM, we are going to give all the weights to the errors, right? And it's going to be equally weighted. Whatever error we have, it's going to be equally weighted. We are not going to give them different weights, each observation different weight. Another difference between GBM and AdaBoost is that, unlike AdaBoost, each tree can be larger than a stump. So we can have, for example, a larger tree with depth of 2 or 3, but we don't make it too large, right? Because we want to keep the trees small. Why? Because we want to make sure that the model variance is low. So remember, in boosting in general, we started from a low model variance but a high model bias, and the goal was to reduce the bias of the model, right? So by fitting a small tree to the residuals, the GBM slowly improves f hat in areas where it does not perform well. So at the end of the day, you're going to get something like this. So let's show it with simple y, because this is a regression. Your overall regression is going to be a function of, for example, the first y hat that you got plus some, let's say, coefficient multiply another, your second output, which is r hat 1, your third output, which is r hat 2, and etc. Right? And we're going to aggregate like this. So this is how the GBM works for regression. For classification, the structure is the same, but instead of working with label 0, 1, we're going to work with probabilities. Because remember, guys, the weak learner in GBM is going to be decision trees, and the outcome of decision trees are probabilities, right? So we can say, for example, if you have two classes, blue and red, each prediction is going to be something like this. For example, this observation to be classified as blue has 89% probability, 50% probability, 31% probability, right? So the outcomes can be probabilities. So these are continuous numbers, and we can exactly treat them as a regression model, right? So we can calculate the residuals. So y minus y hat, let's say class blue is 1, so it's 1 minus probability of class blue for observation number 1, let's say 80%, so we get 20%. So at this stage, we're going to work with continuous numbers. So these are going to be the probabilities, and the rest of the process is going to be exactly the same for regression analysis. All right, so this thing, when we're aggregating over all these trees, we call this lambda our learning rate, right? So the learning rate shrink the contribution of each tree. So these trees are going to be contribute to the final output, and this lambda is going to shrink that. And of course, there's a trade-off between learning rate and the number of trees. If the learning rate is smaller, we are going to have more trees. If the learning rate is larger, we're going to have fewer trees, right? So learning rate slows down the process even further. And this is important because it allows for more and more different shaped trees to attack the residual, right? So because at the end of the day, remember, if this lambda is very large, so we're going to end up with, let's say, 2, 10, or 20 decision trees, right? And maybe that's not big enough to capture all the nuances with the features. Imagine we have hundreds of features, and remember, the first tree is going to be a small one. And in order to make sure that all the features have enough chance to show up in the following models, we need to make sure that the lambda is small enough, right? We're going to work with different variation of the trees, and those different variations are going to attack the residuals. So this is the big picture of gradient boosting machine. So this learning rate is going to be one of the hyperparameters that we need to tune in GBM, right? Usually we start with a very small number because we want to make sure that the tree growing process is done slowly, and we are going to have hundreds or thousands of iterations to make sure that each feature is able to get enough chance to show up in the final model, right? Because what if we have thousands of features, right? Remember, these GBM boosting methods in general start with a very small tree. So if you have thousands of features and then you start with a tree with only 2 features, then we need to make sure that all the features get enough chance to show up in the final model. So for that reason, we're going to start with a very small lambda, and then we try increasing it and basically find the optimal value for lambda, right? The aggregation is done by adding the first 3 predictions and the scaled version, the shrunk version by lambda of the following trees, right? So we already talked about this one. Okay. All right, so let's finally talk about XGBoost, Extreme Gradient Boosting. So XGBoost is a refined and customized version of gradient boosting decision trees. And so it's not like AdaBoost, it's just like GBM, gradient boosting. And it was created with 2 things in mind. 1, the performance, and 2, speed. Because remember, in GBM, we already discussed that if lambda is small, we usually start with a very small lambda. And if lambda is small, the problem is that it's going to take a very long time, right? At least compared to other models, to XGBoost. So we like the idea of GBM, but we want to make sure that we can have performance and speed at the same time. So how can we speed up the process? So that's the idea, the motivation behind XGBoost. So basically, it was designed for faster calculations. So that extreme, refers to the fact that the algorithm and methods have been customized to push the limit of what is possible for gradient boosting algorithm, right? Mostly focusing on the speed part. Now let's compare, again, I'm trying to give you the big picture. The mathematics behind it is of course a lot more involved, but hopefully I can motivate you to go ahead and read the mathematics on your own. So these are the advantages of XGBoost over GBM in general, right? So let's start from the right-hand side. The first one is going to be the inbuilt cross-validation capability. So what does it mean? We know that to avoid overfitting, we can do, at the end of the day, we can use cross-validation and tune the hyperparameter of the model. But in XGBoost, in order to do that, instead of waiting for the model to be trained and then go back to do the cross-validation, it's going to do the cross-validation at each boosted tree. So at each sequence, this cross-validation is done automatically. So without the model being completely trained, at each sequence, the parameters, the hyperparameter is going to be optimized and the optimized version is going to be worked for the next sequence, the next tree, and etc. So this is going to save us a lot of time down the road. The next one is efficient handling of missing data. So in general, to reduce data sparsity, remember, if the data is high dimensional, this sparsity of the data is going to become a big thing, right? Because the curse of dimensionality will kick in and it's going to basically affect the performance of the model. So to reduce that data sparsity, XGBoost can automatically and efficiently handle the missing data during the process. So this is another big advantage. The third one is going to be regularization. This is, in my opinion, one of the biggest advantages of XGBoost over boosting models in general, because the regularization is not just a standard regularization that we have seen in tree-based models, like cost complexity pruning or regularizing the max depth of the tree or max terminal node, and etc. This is something on top of that. Actually, XGBoost is going to do this by adding a regularization term to the loss function. Right? So let me actually write down a loss function. For example, we have, let's use blue. Imagine there is this objective function that we have in mind. And we are trying to minimize the loss function, right? We are minimizing our loss function. And in general, the loss function, so let's say it's a function of, let's keep it very simple. It's a function of summation of y and y hat, right? And so we know different functions. For example, if it is regression, we look at the mean squared error, and etc. But here, let me use another color. In XGBoost, we are adding a penalty term to the loss function, and it's something like this. let's say it's a function of omega, and that omega is a function of number of terminal nodes, right? So it's going to, and this loss function can be something like L1 or L2 norm of the function, right? So for example, we have different weights for each terminal nodes, and we can use L1 norm, the summation of absolute values of weights, or we can use L2 norm, the summation of weighted squares of all those weights, right? But regardless, the idea is that it's going to penalize adding each tree by controlling, by using this omega function, right? So basically, this is something like exactly what we did in regularizations, the penalized regression models, right? So on top of standard regularization that we have seen in decision trees, XGBoost is doing this kind of regularization. So for that reason, it's also referred to as regularized boosting techniques. So it's doing regularization at two levels. First one for the standard tree-based regularizations, and secondly, using L1 and L2 norm of basically a function of weights in the terminal node. So it can handle that kind of regularization as well. The next advantage is cache awareness and out-of-core computing. So this is basically where the speed happens, right? So if you want to say that XGBoosts are fast, this is how it's going to do the job very fast. The idea is that we know CPU is fastest on cache memory, then on the main memory, and then on the hard drive, right? XGBoost is going to run the gradient calculations in cache memory instead of reading the data from the hard memory. So out-of-core computing is an optimization that is going to take into account the hardware itself, right? So instead of reading very large data from hard drive, which is going to take time, it will decompress the data from hard drive and then use cache memory for calculation. That decompressing part is going to take time, but it's a lot less comparing to read the entire data from the hard drive. So it's going to spend a little time on decompressing the data from hard drive, but after that, it's going to be super fast because we know CPUs are very fast on cache memory. The next one is the tree pruning process. XGBoost uses depth-first search approach, which is genius. Let's talk about it. Well, we know that in GBM or AdaBoost, these sequential models are going to stop splitting a node when it encounters a negative loss in the split. So what it means that the GBM, like decision trees, these are the greedy algorithm. It means that it's going to stop whenever the loss function is negative. Well, it faces a negative loss function, and basically that split was not that helpful, so it's going to stop there without looking ahead what's going on. Maybe there's a very good split down the road, which we are simply ignoring it because we hit a negative loss in the split, right? However, XGBoost, on the other hand, is going to make the split up to the max depth specified, right? So that's why we call it, depth first. So let's say the depth of the tree is, you specify it as 10. So it's going to go all the way down to the depth 10, and then when you see all the potential good splits down the road, then start pruning it back by just pruning the weakest, let's say, link, right? So this is how fascinating that the XGBoost is going to work backward and remove splits beyond which there is no positive gain. So and that's why it is more efficient and more the performance is better compared to the other boosting models. And the last one is the fact that XGBoost can parallelize the tree building process, right? So XGBoost implements parallel processing, and for that reason, it's going to be a lot faster compared to GBM. And so this is something that we had in random forest as well. So one of the advantages of random forest was that it's parallelizable. But the neat thing about XGBoost is that, XGBoost is working with sequential trees. So if you think about it, it's going to be very challenging. How is it even possible to make a sequential process parallelizable? One part of it is done in some other core, another part is done in another core of a CPU. So this is really fascinating idea by XGBoost, that it's able to parallelize the tree building process, even though we know that the model is boosting, right? It's sequential. Okay, so these are all the advantages of XGBoost and what makes it super exciting and interesting to work with. Okay, so now let's put it all together by looking at the performance comparison using scikit-learn's make classification dataset. So this is a dataset that comes, this is a toy dataset that comes in scikit-learn. And imagine you're working with 1 million randomly generated data and there's only 20 features. So this is relatively low dimensional data, but the number of observations is relatively large, let's say 1 million. And now we are comparing 4 different models, XGBoost, gradient boosting, random forest, and logistic regression. So the logistic regression is going to be our very simple linear model, and then this is the most complicated one, right? And then remember, 1 million observations, 20 features. So there are 2 things that we want to pay attention to simultaneously. One, the performance of the model. In this case, we're reporting the area under the ROC curve. Right, so we use it as a prediction power. And the second one is speed, right? So the training time, how long does that take for the model to be trained? So starting with the very bottom, let's start with the logistic regression. So it seems that the logistic regression, we get 93% in terms of area under the ROC curve. And it takes 17 seconds, right? So it's pretty darn fast because it's a very simple model, right? Everything is linear and the calculation is going to be super fast. But the performance is about 93.7%. Then the next model is random forest. Random forest is going to easily outperform the logistic regression, as we can see, but it's going to take a lot longer, right? It's going to take 424 seconds. Then the next step is, let's use GBM, gradient boosting. Gradient boosting is going to improve the performance slightly, but in terms of time, it's going to do a very bad job. It's going to take almost 2,000 seconds to just simply train the model of 1 million observations. And this is not a large number, right? So we like the accuracy of gradient boosting, but we really do not like how slow it is. And then that's where the XGBoost is going to shine. XGBoost is going to perform as well as accurate as gradient boosting, but look at the training time. The training time is only 24 seconds. So if you want to compare, if you're only interested in the prediction power of the model, definitely XGBoost is the winner here, because both in terms of performance, let me use another card, compare the performance of XGBoost with logistic regression. Performance is a lot better, and in terms of training time, it's going to take only 7 seconds more for 1 million observation, right? And we know that, coming up with better models down the road which are more powerful in terms of speed, it's just inevitable. It's just a matter of time. So we may prefer a model which is more accurate, even though it's going to take a little longer, because we can deal with that timing part later on, right? However, if you're looking into, for example, having a model that it's interpretable as well, then the logistic regression is going to be a lot more interpretable than XGBoost, because after all, this is the logistic regression is parametric. There's a functional form that you see, you can interpret things, but for XGBoost, it's non-parametric, and basically you're going to be kind of lost in those hundreds of sequential trees. Okay, and in terms of development of all these decision tree based models, we started with decision trees themselves. We like the advantages of that model. We said that, okay, how can we improve the accuracy of the model? How can we reduce the model variance? We expand the idea to bagging, and bagging by using the bootstrap aggregation, we were able to reduce the variance. And then we decided to decorrelate the trees even further, so that's why we talked about the random forest. Boosting and gradient boosting, they attack the model variance from a different perspective. They started with a very small tree and then tried to just expand that tree in a smart way. So they try to start with a very small bias, small variance, model variance, with a but high model bias, and then try to reduce the model bias. So then we had boosting, gradient boosting, and now the XGBoost, right? Finally, in terms of where we are today, it depends on when you're watching this video, right? So as of now, this is 2021. There are some other extensions to XGBoost. So for example, Light GBM and Cat Boost. So these are, so Light GBM, well actually XGBoost itself was developed in 2014 and it got famous in 2016. Then Microsoft released the first stable version of Light GBM in, I think it was around January 2017. And then later on, a couple of months later, the Yandex, it's a Russian lead tech company, it open sourced the XGBoost. And so these are the more advanced boosting models that it's used today. And maybe in the future, not maybe, it's just a matter of time. In the future, we're going to work with even more fascinating advanced version of these models, right? And but the difference between XGBoost and Light GBM and XGBoost is mostly in the structural differences and basically in how they handle categorical variables. For example, when it comes to finding the best first split to work with, Light GBM has a very unique method of finding that first split to start with, compared to XGBoost and XGBoost. It's going to be more efficient and faster. And when it comes to handling the categorical data, XGBoost is going to be a lot more efficient and user-friendly. Well, by user-friendly, it means that it requires less pre-processing compared to the Light GBM and XGBoost. Okay, basically, you're able to handle numerical values and strings for categories in XGBoost, which is not possible with XGBoost or random forest or tree-based models in general. So we know that for auto models, we need to perform various encodings like label encoding, mean encoding, or one-hot encoding before supplying categorical data to the model. But for XGBoost, we can skip that part. So these are the most advanced developments of the boosting method so far. But again, depending on when you're watching this video, there might be even more complicated models out there. Okay, so let's wrap up this very long video by going over the pros and cons of XGBoost. So in terms of advantages, I think we already talked about it. That what are all these features that we explain about XGBoost, these are advantages of XGBoost over any other tree-based models, right? But we know that all these good things should come at a cost, right? You shouldn't get anything for free. And the cost is basically the XGBoost is more difficult to understand, it's more difficult to visualize, and of course interpret. Tuning the hyperparameter is going to be challenging, especially if you're not an expert, because there are lots of moving parts, right? Everything is going to have its own hyperparameters, and you need to make sure that you understand what you're doing when working with the XGBoost. So if you're an expert, go ahead, use XGBoost, make sure that you understand all the hyperparameters. But if you're not, so I think your next best choice is going to be random forest. I personally really like random forest model in terms of model performance. And if your data set is not large, it's not real, and by large I mean really large, I'm talking about terabytes of data, then the random forest may be able to a very good choice for you, because I personally, when it comes to feature importance, I think that random forest feature importance is more stable, at least for the use cases that I use in finance, I mean, compared to XGBoost. Because it sums over larger trees instead of sequential trees. So I think their feature importance for random forest is more reliable. But again, that's to be confirmed. However, I think I really hope that you enjoyed our journey in decision tree-based models, and you enjoy the beauty of it. Until the next one, take care.